This class is about imaging, right? So there's lots of ways you can interpret this term, and we need to come up with a concrete definition of that. So this is an image that you are seeing because light is hitting your retina. That's being reflected off of this diffusive screen, and that is showing a square box that's being projected from the projector that has its own mechanism of display of my dog. There's different ways to interpret what this, pattern of light that's reaching your eye is. So you can think of it qualitatively, right? An image, and this is totally fine to say this as the definition of an image, is just a recreation of some visual scene, right? Optically or otherwise, that can be interpreted as an image. It can be thought of as further downstream than the actual light hitting your eye or hitting the screen and reaching your eye as an impression, right? So some sort of computational post-processing of what's hit your eye that then, exists in your brain can also be thought of as an image. And that's something we'll talk about as we get into the processing of images, quantitative images. And even further downstream, it can be a representation or an idea. So past the impression stage, further up the computational pipeline, in your head, there's some structural way of categorizing that image or connecting it to other thoughts that can form this idea of an image, right? So these are all qualitative ideas, right? We're not going to talk about images qualitatively in this course anymore. They're quantitative, right? So when I say image, I really mean something that's physical and then digitally transduced, right, eventually. So to really talk about images in the context of what we're discussing for our class, we need to think of an imaging device, right? So something that forms an image. So for you all, your eye is forming this image, right, on your retina. But generally, when you take a picture with your phone or any other type of imaging system, there's going to be some sort of element that collects radiation and then sends that radiation to some plane where the image is formed, right? So there's some mapping from the physical world to some plane where the image is going to reside. And so what I'm really talking about when I say the word image is what's occurring here after some radiation has been collected and then effectively focused to some plane of interest or plane of electronic transduction or plane of sensing, whatever you want to call it. But it doesn't have to be so abstract or complicated. So I remember doing this in high school physics, not with a candle. I think that would have been like a no-no, but some little electronic light bulb. We had a lens, and then we put a piece of paper on a clip, and we moved the piece of paper around until we saw a picture of that little light bulb, and the picture is inverted, right? Just like the image of the world on your eye is actually inverted, and our brains flip it over. So that is a image, right? A physical image. It's hitting the paper, and then you can see it being formed, right? And then on the right is an image. You can kind of see a building upside down, perhaps. So that's an image that's being formed not by a lens, but by a pinhole, a small hole, right? And so you can all just make a small hole in some piece of paper or cardboard. This is in the wall of a church. And then there's an image of the world outside of that dark room within the church. Again, upside down. They always flip upside down. And so this is this idea of a pinhole obscura, which many people, I think, kind of agree now that artists would take advantage of to make high quality paintings historically, right? Sort of cheating by tracing out the actual image, but with paint or drawing. So they can be physical, right? And just be very tangible. So don't be worried or scared of images. They exist around us. So what we'll do starting this class, next couple classes, is come up with a mathematical description of images. And so we will model how radiation, essentially maps from the real world to this plane of interest where the image is formed. And we'll describe it as an intensity, I, right? And that intensity is a function, right? A mathematical function. It's a two-dimensional function, right? Its coordinates are of x and y. The two dimensional coordinates that define the image plane over there where my dog is. And so that's a continuous function. It's unbounded, right, effectively in x and y, unless we define bounds on it. But it has certain properties, right? It's a non-negative function, right, which is useful because intensity, energy, right, intensity can't be negative. So there's certain properties of that. That will then, next class and the class after, discuss how it's actually represented not physically as a continuous signal, but actually digitally. So there's a process of digitally converting that physical, right, radiation into an electronic signal, digitization process. It's not just with light, right, but it's with ultrasound, it's with MR, it's with CT. For the purposes of this class, right, almost all images that we care about are going to be digitized eventually, right? Because otherwise it's really hard to apply machine learning methods to them unless you're super fancy and have some like photonic neural network in your back pocket, which is not easy to find. We are going to be using electronic computational software to process these, and so we need our images in a digital form to then enter our computers for processing. Okay, so there's this process of forming a discrete image, which we'll go over. And then once it's discrete and digitized, we can work with it, right? And so the images that we'll end up with are going to be two-dimensional functions, discrete functions, also non-negative generally, that are defined by coordinates x and y, which is the plane of interest that the radiation has hit and then been digitally transduced into an electronic signal at. But here over on the left, I drew an array of little boxes, and I put a picture of something that looks shiny, like a chip, right? So the boxes represent pixels. Generally, people use that term now, not just for optical image sensors, but many different other types of sensors for other types of imaging devices. And the chip there is an optical image sensor, right? So what's called a CMOS image sensor, if you've heard that term. And so these CMOS image sensors, that little chip there is it's sometimes a millimeter by a millimeter. It can be up to a centimeter by a centimeter sometimes, and they're everywhere, right? They're in all of your pockets, I promise you, because I know all of you have smartphones. I would be surprised if one of you didn't have a smartphone, actually. You might. A friend of mine recently converted to having a flip phone because he got tired of being distracted for his New Year resolution. He bought a flip phone. And some of those actually have these in them, right? Even if you have a flip phone, it sometimes has a little low quality digital camera in it. These are plots of the number of those sensors. Plot in the upper left goes up to 2015. And it's the number in the red column of these image sensors that are in phones, right, in smartphones. You can see there was an astronomical or exponential-ish rise in that, not surprisingly, starting around 2009, up to 1.5 billion. I think this is created per year. So that's a lot of those little chips out there, just in smartphones. The blue curve at the bottom, you'll see, is the number of digital cameras that weren't smartphones. So these are these point and shoot cameras, which, pre-2009 were kind of ubiquitous. People had those, or they had film cameras. And you can see they've died out pretty much. Since 2015, that blue thing has likely gone down a lot. And then the lower plot goes up to 2021, and it kind of continues to show what happened to the number of I could only find smartphone image cameras. So it plateaued at around 1.5 billion per year. That's sort of the saturation point of, I guess, our consumption of smartphones, right? The world's consumption of smartphones. But that's a lot. If you integrate that, it's way more than the number of people in the world, right, at this point. So we're at the point where there's, even just in smartphones, way more eyes, right, taking pictures than human eyes, effectively. Albeit we have two, I would argue that many current smartphones have 2 or 3 now. And so counting those, I would put my money on there being more smartphone digital cameras than human eyes in the world. That's just smartphones, right? And so this plot on the right shows just sales of the sensors themselves, light sensitive image sensors, right? The CMOS sensors. That's still increasing linearly. And so that means smartphones have saturated, but these image sensors are now being put into all types of other devices, right? So that includes at the hospital, right? In medical scenarios, surgical ORs are being outfitted with lots of cameras, endoscopes are having digital cameras, autonomous vehicles, right? As I'll show, you name it, they pop up in all sorts of places. So I don't know when this is going to stop. I don't foresee it stopping anytime soon, because the richness of the data you get from an image is great, right? It's a lot of useful data. Our software that we now have is really effective at processing that, and they're cheap, right? These chips cost less than $1. Why not just add one to whatever device you're making? Yeah, we're up to 10 billion image sensors being created per year. Where are all these image sensors going, right? This is a market. There's many markets, but I just showed here on these newer vehicles, not even that new. Like I have a 2017 car, something like that. And it definitely has at least 4 cameras, because I see a forward-facing one, a rear-facing one. Maybe there's definitely 2 high-quality cameras. So newer cars here, I circled in red the cameras, and I just like randomly selected a car. But the red circles I put are actual image camera, like image sensors, like in your pocket in your phone. Then there's also these interesting image sensors that are called radar, which are more likely LiDAR-based systems. I perhaps think this is a mislabeling. So there's other types of image sensor that aren't just the standard optical image sensor, which we'll talk about later in this class, right? So there's newer types of image sensor, even just on these cars. Another example is in surgical robotics. These are great applications of cameras, right? These are highly integrated with imaging and optics. I know that because these companies heavily recruit people who, or they ask me for people to hire, right? Because they're in desperate need of people who know how image data is acquired and how to process it and stuff like that, right? There's naturally a huge market for these in new smartphones, and not just for regular cameras, but for these LiDAR type cameras, LiDAR standing for light detection and ranging. So it's a process of shooting pulses of light out and then waiting for how long they take to get back, just like in radar in the old movies, right? But now just with light instead of radio waves, to form these 3D pictures of the world. There's actually some really great apps. These are all on the newer iPhones and the new iPad. But the third-party apps you can download to do this are really cool. You can walk around and just map out this whole room in 3D and then navigate through it 3-dimensionally. If you have the newer iPhone, I definitely recommend you download and try that. And so I guess what will happen in the next few years is that we will be consuming not just 2-dimensional images very much, but more and more so 3-dimensional images, at least at a macroscopic scale, right? And so this class will talk mostly about 2D image data, right? The kind of images we're used to seeing on our phone, but I want you all to just be aware and think about, hey, it's not just these 2D XY representations that will be important going forward, but it's really 3-dimensional data that's also available. So here's a picture of my dog, the tip of the ear, I think, zoomed in. And so if you've done this, it's kind of hard to do this on your smartphone, but when you zoom in, because it kind of interpolates. But if you download an image onto your computer and use, let's say, ImageJ or some other more scientific image viewer to zoom in to an image that you've captured, if you haven't done that yet, you should. What you'll eventually see are these little boxes, right? These little squares. You can't keep zooming in, I promise you. This isn't CSI. You'll eventually see little boxes which define the resolution of your image. Those are the pixels I'm talking about. And you'll see visually that there are different colors, right? Or different hues, different brightnesses. I picked a region in this image that was more black and white to make it a little simpler to explain. If you're dealing with a black and white image, then those different brightness values are directly mapped to numbers. And so this set of 3 by 3 pixels, each of which detected a different amount of light, just you can directly translate into a different number. If the pixel is lighter towards white, it's a larger number. Then if it's darker, it's a lower number. Right? Generally, most images you're going to capture, the number scale ranges from 0 to 255, or 0 to 512, sorry, 511, or 0 to 10,023. Going beyond that is a little advanced, but some phones do that under certain features. But that's what we're dealing with. So when I talk about an image as a quantitative thing, this is what I'm talking about. It's a matrix, right? An array of numbers. So that's a discrete representation of this thing we generally think of as a continuous sort of physical quantity of light or radiation, right? And so what's the bridge between the physical quantitative image that's hitting a wall or hitting our eye and this array of numbers? It's defined through a mathematical process, which we'll go through in a couple classes, called the sampling theorem. And so we'll make sure we really understand that to cover this bridge between digital and physical. Okay, so once we have that array of numbers that we've captured or that we have downloaded, we will then use mathematical operations to prepare it for our machine learning analysis. And so we'll take generally these two-dimensional arrays, and at least in this class, when we're talking about them, we'll often abstract them away as vectors. Why? Because vectors are so easy to manipulate mathematically and write simple equations to define. So that's something we'll definitely do. And you can do all sorts of different ways of you can either convert the two-dimensional array of numbers into a horizontal vector, or which is a row vector, or a column vector. We'll mostly be using this definition of taking a two-dimensional array of numbers and taking its columns and stacking them on top of each other to form a column vector. Okay, why? Because if you've done any linear algebra, column vectors are kind of always the variable of interest, right? They are at the end of our linear set of equations that define what's coming in to our linear system. So if that's news to you, then you should start reading a bit about linear algebra. The Gilbert-Strang book's a great one, but hopefully you're comfortable thinking about a vector of numbers, right? And how we can manipulate that vector of numbers. So what manipulations are possible? We can add images together. That's a simple one. We can multiply them. So this little circle with a dot in it is called a Hadamard product, or an element-wise product, where you just multiply each element of the vector with each element of another vector directly, one by one. And this is really the key one. We can perform a matrix vector product, right? Of matrix multiplication. So we can pass that vector through a big matrix, a two-dimensional matrix, and come out with a new vector of interest. We can perform nonlinear operations as well. We're not just confined to the linear world. We can square each element of the vector. We can perform other nonlinear operations like a thresholding or a sigmoid type operation, if you've heard that word. That's what neural networks do a lot in a cascaded fashion. So we'll be doing that. And then you can convolve two vectors. This bottom one, we're going to be doing a lot. Convolutional means we're doing convolutions. So we're going to get good at those. So just to show you a convolution up front, because you're going to see it like 6 times, and I know some of you haven't seen it. A convolution is a mathematical operation where you take an array of numbers and you essentially mix them together locally to create a new array of numbers, okay? And so mathematically, and again, we're going to go over this in detail, so if this is all like, wow, it's fine. This is just an overview to get through the main ideas of this course quickly, and so they're in the back of your head. The mathematical definition of a discrete convolution is on the right. That's convolving a vector I1 with a second vector I2. So this top vector I1 represents our image, right? A set of pixels, right, that we captured with different brightnesses that have a number to define each brightness. The second I2 is generally what's referred to as a convolutional filter or a blur filter. People also call it a kernel or a blur kernel. So when we perform this mathematical operation, it looks kind of complicated, right? You have this indexing number n, which defines each entry of the output vector that we're creating. And then there's this m number, which is being subtracted. So this m variable effectively defines the extent across which we're mixing the numbers. And so when we want to perform this mixture, we'll start with you can think of it very kind of graphically. I like to think of it graphically, at least. We start with the vector over on the left side, and we're gonna multiply I1 and I2 across each location. And so what we'll do is we'll multiply 17 times 1. I started with 1, 1, 1, because it's very easy. We'll multiply 17 and 1, and we'll multiply 21 with this one, and we'll multiply 24 with this one. And then you'll see there's a sum, an addition, right, in the equation. So we'll add all those up. So the product of 17 and 1, and then 21 and 1, 24 and 1, summed up is 62. That defines our first entry of our output vector. Then this graphical representation is nice because what you do in your head is you slide that over one spot. So I've slid it over, and we'll repeat that process. We're going to multiply 21 and 1, 24 and 1, and 20 and 1. Add those up. You get a new number, right? And you just repeat that process through the whole vector, and that's your convolution. And so you can very quickly observe that that process is mixing all the values in our vector together, right? The three values on the left kind of got merged together to form a new value. The next three values got merged together to form a new value. When you think of that in terms of images, that, if you think about it for a second, makes one image, after you've convolved it, a blurrier image. You've mixed all the pixels locally if you do this in 2 dimensions. And so really what the convolution is a blurring operator. It takes numbers in little patches and adds them all up, mixes them together, goes to the next patch, adds them all up, mixes them together. And so if you had a nice sharp edge, now you've taken values on one side of the edge and the other, and you've added them together, mixed them all together to make kind of gray value, right? That isn't so sharp anymore. So this blurring operation is really the root or the heart of convolutional neural networks, the heart of machine learning. It loves to blur images, it being the algorithm you're going to make. Because by blurring them, by mixing those values, the computer can start to gain insights into what is exactly in the image. So this is something we're really going to get good at. So here I did in Python a convolution of this image. It's a canonical image people use in image processing world. It's called the cameraman. It's some guy taking a picture out on the lawn at MIT, and I blurred it with 1, 1, 1, 1, 1, 1, 1, 1, right? So we know that's going to make this blurry image. I don't have to just put all ones in this blur matrix. I can put other values. So here I put this set of values, -1, 0, -1, -2, 0, -2, right? This particular matrix takes that image on the left. I'll apply this operation, and I'll create something on the right. Now the person is clearly picked out as a bright value versus the background, which becomes a dark value, right? And so you can pick different blur filters to manipulate the image to really highlight or pull apart different things of interest, right? So naturally, this type of representation on the right, you can imagine would be useful for a computer that's trying to detect people, right? Or detect foreground objects, let's say. Because now all of those people pixels have become bright. And maybe you could then define some additional processing later to say, hey, pull out the bright pixels, perhaps those are foreground objects, right? And so what neural networks do is you don't tell it this set of numbers in the blur matrix. What we're going to do is have the computer determine values of this matrix that are optimal for specific goals, specific tasks, right? So these W's we'll be using a lot. They're called weights. They're neural network weights. They're just numbers that the computer can figure out. And once they're figured out, then they're just kind of set and used for these different tasks, right? For the task of, hey, segment out people from the background, or tell me, put one type of image in category A, let's say it's healthy, an image of a healthy patient, and another type of image in category B, let's say it's an unhealthy patient, right? So tasks like that. So the principle of convolutional neural networks really is a kind of set of equations where a computer has figured out ideal weights W that it'll use to blur an image, usually in multiple steps, to then create a final vector that is able to be utilized for task-specific purposes, right? Purposes we really want, right? That will benefit us. Okay, so like I said, we really want to determine these weights, and the tasks are up to us, right? So we can say, hey, we want to segment an image. We want to detect some object of interest, draw a box around it, and follow it through a sequence of images, right? You can convert images to color images. You can, really the sky's the limit, right? There's all these abstract ideas that we can attempt to achieve with artificial intelligence type processing of images that we need to define up front. And then you go about trying to do it. That's the second problem we can talk about. So what are some common goals that we can try to achieve, right? Kind of in this class, I guess, what we're going to really focus on is transforming images first into a vector where each entry of the vector is assigned a category. So that goal is called image classification. And so we can define a vector, let's say, where the first entry, it's a 2-entry vector. If the first entry is 1 and the second is 0, then that image will be classified as a man. And then the second could be a dog, right? And we'll have images of men or dogs that be presented to the computer. And I'm just picking that because there's a man there, and I just came up with that random example. But, we can define that as however we want, right? And so something we'll be working on in this class for classification is looking at images of cells and categorizing them as the cell type, right? So is this a leukocyte or a lymphocyte, right, etc. So, but there's many, many examples of that, right? Classification. It's probably the most common use of machine learning for image analysis, just historically. Another great application that we will use in this class is to do object detection. And so in this setting, we input an image, and then the output is going to be a box where the box is around some feature of interest. So we could say, okay, always draw a box around some subject's head, right? This person's head or any subject's head in the image. Give me the image as the output with the box around that. So then it's highlighted. And then a third is segmentation, which I already mentioned. So you can draw a boundary around whatever you're interested in. We'll cover that case as well. There's many, many other situations, but those are the 3 main tasks we're going to be focused on in this class. Okay, so connecting the 2 topics is really the goal of the final project in this course. The first topic being how an image is formed, and the second topic being how we then, can process that image to achieve certain goals. So we can really put these 2 ideas together pretty easily. we have a physical world where perhaps this person is. We have a imaging element, and then we have an image formed, right? And so it shouldn't be so surprising, and we'll define this very carefully, that we can create a mathematical equation that describes the process of image formation, right? From physics and just our insights, we can say, hey, if there is this physical representation of the world, we can define it as a vector, I0. It'll then be manipulated by the imaging device, by the propagation of light to the imaging device, from the imaging device to the sensor, et cetera. That can be all defined generally by a linear operation, which can be a big matrix, W0, right? Generally, we'll be doing linear image transformations, right? Optics and many kind of related disciplines mostly behave linearly, or if they don't, then we'll just make assumptions to make sure they behave linearly, because then things get simpler, and we'll get an image. So this image will then be manipulated by the computer. And so there'll be some other set of operations once the image has been formed to then get to our final goal, right, which I just described. And I'll just really, and it's not, this is like a very poor approximation, but let's just call the set of operations that the computer does a set of linear operations W1. They most certainly won't be linear in this class for the most part. So I'm just using this as a very simple example. We can combine those two operations together. We can say the real world is connected to the output of our machine learning network via a longer equation, which combines the operations that define what's happening to our radiation before the image is formed, W0, and what's happening from the digital representation of our image to our final machine learning output, W1, right? And so we want to consider that holistically in this course. Why? Well, I'll give you lots of examples of why. A, because it yields the ability to do new things in imaging and analysis. B, you can create new types of image detection hardware or methodologies that can be beneficial, work better, cheaper, faster, whatever. And C, because it's really interesting and fun to do. The equations we'll eventually get to, and I'm not going to dwell on this right now, are going to be a cascaded series of linear and nonlinear equations, right? It's not going to be some simple combination of two linear matrices that are going to define our mapping from the real world to the machine learning task. It's going to be a cascaded series, right? Where T is some nonlinear transform and W is a linear operation, right? But we'll define this very carefully. This is where this idea of convolutional neural network comes in. It replaces that simple linear convolution I was showing that took the image of the man and made it bright in the foreground and black in the background with something more complex, a little bit more abstract. Fundamentally very similar, but a little bit more complex. Right? And so it's not too scary of a term. It's just that idea with a little additional stuff added to it. Okay. And when you see pictures like this in the future, you're not going to be afraid, because we're going to really simply define what these complicated diagrams that you may have seen before in papers or online that talk about machine learning, what they actually mean, right? They're simply a cascaded series of convolutions with nonlinearities applied in between each convolution, right? But we'll become quite good at these types of diagrams. Okay, and so really what we're going to do is try to optimize all of this whole transduction and processing procedure together. Or I'd like everyone to consider that or understand how that's possible, right? And we're going to think about that holistically for our final project, right? Or I'm going to encourage everyone to think about that holistically for your final project, right? Because it's very easy to start here and say, hey, I have some images, and I can download some neural network and start to process them and classify them, right? There's thousands of resources online to do that already. But you can also consider what's going on as those images are being acquired, or how they were acquired, or new ways to acquire them, right? And that's a very simple mathematical addition you can add to your machine learning structure that opens up a lot of interesting insights.